Now let's see the strong conditions using eigenvalues to tell whether the Jacobi iteration is working or not. Okay, so use eigenvalue to see the Jacobi iteration is working or not. Stability. Okay, and we have our system which is AX equals to B. If we can write our A matrices to be three components, which is the diagonal component, the upper triangular, and the lower triangle, then we can rewrite our system to be a D plus U plus L times X equals to B. And this A matrices can be write like diagonal, lower triangular, and the upper triangular. Then we can write our system to be this system set, right? And we can also write our iteration, the Jacobi iteration using this format as well. So if we can write in this form with our AX equals to B, then our DX will be equals to B minus UX minus LX. Okay. And after that, we know that our X will be equals to D inverse B minus UX minus LX. Okay. So, and we can write this as a Jacobi iteration. Jacobi iteration where xk plus 1 will be equals to D inverse B minus U xk minus L xk. Okay, so that is actually the Jacobi matrix's form of the iteration part. Then let's do the arrow analysis. Arrow analysis. We know the exact solution should satisfy this form, right? So x should be equals to D inverse B minus D inverse U plus L times x. So this is the true values should satisfy this equation. How about the Jacobi iteration? The xk plus 1 equals to D inverse B minus D inverse U plus L times xk. Okay, so this is the Jacobi iteration. Let's do a substitution. Let's do a subtraction between the exact solution and the Jacobi iteration. Then you can get the arrow of the next step arrow and the current step arrow. So for the arrow, which is using the exact minus the Jacobi iteration, so 1 minus 2, what we can get is x minus xk plus 1. That will be equals to D inverse B minus D inverse B should be cancelled out, will be 0. Then it should be minus D inverse U plus L times x minus xk. Okay, and we can use the arrow to represent this arrow is at next step. This is the current step arrow. So arrow at next step will be equals to negative D inverse U plus L times the arrow of the current step. Okay, and then this part you can say this is a new let's say just E. This is our E. Okay, this new matrices, so the arrow for the next step will be equals to this E matrices times the current arrow. And this go to our eigenvalue, eigenvector problem. So you can think about your arrow 1 will be equals to this E times at arrow at 0 step, and that will lead to eigenvalue times x0 So arrow 2 will be equals to this E times arrow 1 will be equals to E times E squared arrow 0 at 0 step. That will be lambda squared at 0. And then you can do until this arrow at the n step. That will be equals to E to the n times arrow at 0 step. It's lambda to the n step times arrow not at 0 step. So only when your lambda is smaller than 1, the absolute number is smaller than 1, that will lead to a stable system because your arrow is converged to 0. Because your arrow is converged to 0. Then if when your lambda is over 1 or 1 of the lambda is over 1, that will lead to unstable system where the absolute the arrow of the k step will converge to infinity. So we can use the eigenvalue of these E matrices to decide whether the system is stable or not using the Jacobi iteration. Okay.